Hi guys, welcome to my video on tectonic geomorphology. In this video, we're going to talk about how things like precipitation and erosion can control the height, the width, and the topography of mountain belts. And I always like to frame this as a competition between tectonic uplift of rocks, for example along thrust faults, that's acting to raise the elevation of mountain belts higher, versus erosion by way of glaciers and rivers that are cutting downward into the mountain range, acting to lower the average elevation. And we see great examples of this in the Himalaya. In the western Himalaya, in the Karakoram, we have huge glaciers fueled by heavy winter snowfalls. In the eastern Himalaya, we have very powerful rivers like the Sangpo, cutting a deep gorge downward into the Himalaya. And so if we zoom out and we look at that in map view, it really gives you a sense of this ongoing battle. For millions of years, rocks have been being thrust upward and torn down by rivers and glaciers. And this shaded relief image gives us a snapshot or a status report of that battle at this moment in time. And sure enough, we see that elevations are very high because of tectonic uplift. But we also see these deep glacial valleys in the Karakoram range, where the glaciers are working to cut downward. Likewise, we see the Indus River carving a hugely deep gorge as it comes across the active faults of the Himalayan front. So this competition is ongoing. And in this video, we're going to do two things. We're going to look at the feedbacks between tectonics, climate, and erosion, and then we're going to use those to think about this concept of topographic steady state. So who are the players in this battle? Well, the players, as I said, are tectonic uplift, rocks coming upwards along thrust faults to create mountain ranges, often with a steep mountain front. Along that mountain front, we can generate precipitation, focused rainfall or snow. And that focused rainfall or snow can fuel rivers and glaciers to actually erode and work backwards, tearing down these thrust sheets, and in some cases causing them to reactivate. So we're going to explore each of these factors or processes one by one. And we'll start with tectonic uplift. And in this video, we're going to think about tectonic uplift in terms of the critical wedge. And so keep in mind that the Himalaya can be viewed essentially as a thrust wedge. As the Indian plate has gone down to the north, sediments atop the Indian plate have been thrust off and thrust and stacked into a wedge-shaped stack of thrust sheets. Okay, so here's the wedge shape right here. Okay. And that's a cross-section coming across the frontal Himalaya here. Same situation in the Andes. If we look at a cross-section coming across the eastern side of the Andes at about 23 south, we see that the structural geology here is also a wedge. We have a basal detachment with a network of wedge-shaped thrust faults sitting above it, where thrusts have been stacking slices of rock one over the other. So why is the critical wedge concept so important? And let me first say that if you need a review of this idea, please see my previous video on the topic. But essentially, critical wedge theory is important because it determines which faults in the wedge are going to be active, which in turn determines whether the mountain range is going to be high with a lot of activity on the rear faults, or if it's going to be wide with a lot of activity on the faults out in the front of the wedge. And recall that a critical wedge develops first by activity on the rear thrusts. They slip until they can no longer carry the heavy load developing above them. Then a new thrust breaks out towards the front of the wedge, and it slips until it can no longer carry the heavy load. And then another thrust breaks, and another thrust breaks. So essentially we see that thrusts become younger as we go out to the front of the wedge. And if we keep breaking new thrusts towards the front, our mountain range gets wider and generally not as tall. However, if we allow these thrusts in the back to be active, we can make our mountain range taller and not as wide. So how might we make these thrusts in the rear active? Well, keep in mind, they stopped or they became critical because the load above them was too much to carry. So if we actually remove some of that load by erosion, we can drive what's called out-of-sequence thrusting. And we can allow these faults in the rear of the wedge to slip and have the mountain range become higher instead of wider. And a great example of this is the Andes mountain range. This is a compressional mountain range that runs thousands of kilometers north to south. It can be approximated essentially as an orogenic wedge or a critical wedge along its whole length. But notice, the width of the wedge is very thin in the north, then it becomes thick in the middle, and goes back to being thin again in the south. One idea to explain this changing width is actually precipitation. We see that precipitation is very high in the north due to wet moisture coming off the Amazon basin. Likewise, it's very high in the south due to westerlies bringing moisture in the Patagonia region. But the central region of the Andes is essentially a desert, and it's been hypothesized that low precipitation in this region diminishes erosion rates, which forces the wedge to grow wider instead of higher due to the reasons that we just talked about. So essentially, because we can't unload the critical wedge here by erosion, we're forced to make a wider wedge. So now that you understand how erosion of a wedge can control the width of a mountain range, let's look at what those what the processes are that control erosion. And we're going to look at two things, rivers and glaciers. And both of these are essentially controlled by precipitation and slope. All right? This is pretty straightforward. Rivers become way more powerful when you give them a lot of water and steeper channels, just like is happening in this flood in the Western Himalaya in 2015. And glaciers are the same. They're essentially rivers of ice that are taking snow accumulating at their upper high elevation areas, turning it into ice, and that ice then flows like a river down the valley until it melts at the base of the glacier. And it's that flow of ice that drives erosion along the base of the glacier. So if we feed glaciers more precipitation or more snow, they have to flow faster to flux all of that material through the valley. And as they flow faster, they do more erosion along their base. So in sum, both rivers and glaciers are more powerful erosive agents if they have more precipitation and higher slopes. So before I move on, I want to quickly explain why it is that tectonic uplift actually leads to higher river slopes. And it's essentially the idea that as material or rocks are thrust upward along a thrust fault, in this case at the front of the Himalaya, those rocks that are being thrust upward essentially become higher than the basins out in front of them. And so rivers that are flowing off of the thrust sheet out into the basin have to flow downward off a steep mountain front. That essentially makes their channels much steeper and therefore more powerful. And we can see evidence for this by comparing 10 different river profiles, which were all extracted along rivers that flow north to south off the high topography of the Himalaya onto the flat basin. And sure enough, what do we see? Each river is relatively gentle in its upper reaches, and then we see very steep slopes as they flow downward into the basin. And they all tend to have these steep slopes right as they cross the zone of active thrust uplift, or the main central thrust zone. So what we're seeing here is the rivers are working they're working hard to erode down and engage in this battle between tectonic uplift along faults and downward river erosion. But the key idea is that their slopes are steeper, and so they have more energy, and so they're able to effectively erode across the growing thrust faults. And so this brings us to our third category, which is precipitation. So we know that rivers are fueled by precipitation, but how is precipitation actually fueled by mountain ranges or by topography? And this is really the idea of orographic precipitation. Essentially, as moist air masses impinge on a mountain front, they're forced to rise up and over the mountain range. As they do so, they cool and they condense and they drop focused precipitation, rain or snow, right on the leeward side of the mountain range. And then as they continue across and they descend, they're warmer and drier and they don't offer much rainfall. And this creates a rain shadow, which is very typical. A dry area on the back side of the mountain range and a very wet area on the front side of the mountain range. And of course, it's this focused precipitation that fuels rivers and glaciers to drive erosion on the leeward side of the mountain range. And so a great example of this is the Himalaya. This map shows monsoon precipitation during the summer months along the Himalaya-Tibet region. Monsoons are essentially coming from the west and from the south, and as that moist air hits the topographic front of the Himalaya, we get very, very heavy precipitation right up against the topographic front. In this case, the blue colors show greater than 4 meters per year of precipitation. Absolutely torrential rainfall, fueling very violent rivers and very large glaciers. So in summary, let's just recap how all these three components are related. We've essentially shown that tectonic uplift of an orogenic wedge can cause steeper hill slopes and river channels, which act to enhance erosion rates along the front of the mountain range. We've also shown that tectonic uplift can cause orographic precipitation, which can focus more snow and rain along the front of a mountain belt, which also drives rapid erosion. And so if you have a lot of this going on and you have a lot of rapid erosion, that acts to actually remove material from the orogenic wedge and allow tectonic uplift to continue at a higher rate. And it may also allow us to sustain a narrower orogenic wedge if we focus erosion right on the front of it. So there's some very strong feedbacks here, but keep in mind we can also force the system externally. If we change climate, for example, we make it wetter, or we change the pattern of monsoon rain, we can actually directly influence erosion, which can directly influence the pattern of tectonic uplift, okay? So changes in the climate system can directly control tectonics. Likewise, if we build a mountain range like the Himalaya due to an external tectonic collision, that can start generating orographic precipitation, which can completely change climate. So these things are related kind of in an internal loop, but we can also force them externally. And tectonics can influence patterns of precipitation, and likewise, patterns of precipitation can influence the pattern of tectonics. So now that you understand these basic ideas, I want to finish the video with this idea of topographic steady state. And this idea kind of asks the question, all right, what happens if we let a mountain range continue to have tectonic uplift over time, and we have a relatively steady climatic system that's driving erosion over time? And the answer is we can reach a kind of equilibrium or a topographic steady state where tectonic uplift balances erosion. And so this story essentially begins by thinking about river incision. Here's another shot of the Sangpo Gorge as it cuts down through the eastern Himalaya. And what we see is that it's the downward erosion of rivers that essentially sets the pace of landscape erosion. But the key idea is that as this river goes down, these hill slopes become steeper, okay? Especially if we consider the idea that the ridge line is not eroding nearly as fast as the river bottom. The ridge line is kind of moving at a very slow pace of erosion, whereas the river bottom is being eroded incredibly quickly due to this violent river in its bottom. So as the valley goes deeper, the ridge line stays stable, the intervening hill slopes become much, much steeper. And what we start to see are landslides. Notice all these landslide scars along the slopes of the Sangpo Gorge. So on average, as these hill slopes become steeper, they tend to fail by landsliding when they reach their threshold angle, okay? And the threshold angle is essentially defined by rock strength. Stronger rock materials like granite can sustain very steep hill slopes before they fail by a landslide, whereas weak materials like shale, for example, can only sustain very shallow hill slopes before they fail by landsliding. So regardless, as rivers cut down, you're going to eventually have landsliding. But the hill slope angle at which that occurs is different for different rock types. And the key idea is that eventually, if the rivers keep cutting down, we're going to get landslides, which is eventually going to also lower the ridge lines. So if these processes continue over a long time, we're left with topographic steady state. This is a situation in which essentially the form of the landscape isn't changing. The rivers are fixed, the ridge line is fixed, the hill slopes are fixed. The shape of the topography is not changing, but erosion is in fact still happening, potentially at a very fast rate. So we've essentially got the rivers going down and the ridge lines going down at the same rate, and that is exactly compensated by rock uplift due to tectonics. And therefore, the surface elevation doesn't change over time, and likewise, the actual morphology of the landscape doesn't change very much over time. And so it's useful to think about what happens if we tweak this system. What happens if we get an acceleration in rock uplift rate? Well then, the rivers and ridges just respond by cutting down faster to regain that steady state. Likewise, if the rivers and ridges start outpacing rock uplift, they're actually going to slow down because the rivers are going to have lower slopes over time and their erosive potential is going to be less over time, which allows rock uplift to catch up. So we can see that the natural feedbacks built into the system essentially guide the landscape towards this steady state situation. So in summary, this video has shown that the morphology of mountain belts can be attributed to the interplay of tectonic uplift, erosion, and precipitation. We've shown that tectonic uplift is often controlled by the activity of specific thrusts within a critical orogenic wedge. Likewise, the erosive potential of rivers and glaciers is controlled by their longitudinal slope and by the amount of precipitation that's fueling them. And precipitation, in turn, can be strongly influenced by topography through the mechanism of orographic precipitation, where it's focused up against the leeward side of a mountain range. And so we use those ideas to build towards the idea of topographic steady state. And topographic steady state occurs because as rivers cut downwards or in size, the hill slopes steepen and tend to fail at some threshold angle that depends on the rock strength. With each landslide failure, the intervening ridgelines are lowered, which eventually allows rivers and ridgelines to lower at the same rate. If the lowering of rivers and ridgelines is compensated by rock uplift, then the elevation of the landscape and the shape of the landscape may be fixed in what's called a topographic steady state. Thanks so much for listening, and these concept questions will help you think through some of these tricky ideas. See you in class.